Hello everyone, my name is Furkan Guc. I'm a PhD candidate in the MESA Lab UC Merced. Today I am going to talk about our project, Smart Predictive Maintenance and Error Recovery for Transmission Line Effects for RF Impedance Matching Performance. Our outline is as follows. We will start with the introduction of the work, and we will talk on the benchmark RFM problem with the transmission line performance. And we will investigate the performance under noise and performance under certainty for the proposed methodology, and we will wrap up with the conclusions. So, what is RF impedance matching network for our smart predictive maintenance framework? So, RF impedance matching, in the RF impedance matching benchmark, we have RF source and RF load, which should be matched in terms of the impedance to perform the best performance in terms of the maximum power transfer or minimum reflected power. And in this configuration, we have a impedance matching network, which can be consist of different circuit elements like the inductors, variable capacitors, and so on and so forth. In our L-type upconverting impedance matching network, we are solving the feedback problem with the real and imaginary part of the admittance equations in order to match the load impedance with the source impedance. But most of the time, it's not always ideal in the real world. We have additional impedances due to the different effects such as transmission line impedances. And one of the most important components coming as the transmission line impedance is between the source and the impedance matching network, which can be considered as the transmission line impedance. As a combination of the load, impedance matching network, and the transmission line impedance, the resulting matching impedance is highly nonlinear, and it's a function of different properties, including the impedance matching network and also the cable properties. So if you consider the cable properties, you can solve for the nominal cable length in the system for a given system. But for most of the time, it's almost very hard to play with the same transmission line for different conditions because our load inertia is changing all the time, and it's not always same for the nominal cable length. And for the rest of the work, we define 4 performance metrics. You can see the reflection coefficient and reflected power graphs as a function of time here. And we define 4 performance metrics, including the tuning time, integral of the reflection coefficient, max reflected power, and mean reflected power within the tuning time. And starting with the benchmark RFM problem from literature, we have a nonlinear system dynamics considering the real and imaginary part of the admittance as the feedback variables. And we have a feedback controller, and optimal feedback transformation is the real and imaginary part of the admittance, which is another work from our group. And we are also utilizing the feed-forward controller with a switching mechanism depending on the reflection coefficient. And we try to control this benchmark RFM problem with feedback plus feed-forward control. And if you consider the case 0 with the golden recipe with no transmission line, as you can see, our starting point for the CTCM capacitors is 100%. And we have some performance metrics around 0.97 seconds of tuning time and some gamma integral mean and max reflected power. And if we introduce the Z transmission line effect into the system in the benchmark problem, as expected, almost all of the performance metrics are gone bad. We have a higher tuning time, we have a higher gamma integral, and we have higher mean and max reflected powers. And in the ideal case scenario, again, if we know the transmission line effects, and if we can cancel out with the inverse of the transmission line, we can recover from these negative effects of the transmission line. And simulation results show that by including the inverse of the transmission line, we can exactly recover the golden case scenario without the introduction of any noise and uncertainty effects. And finally, instead of only canceling out the transmission line effect by the inverse of it, what we propose is that we can insert a virtual transmission line which can do better than the previous performance. With the optimal cable length, the virtual transmission line may enable us to have better performance metrics. So if we solve for these and we can try to find the best optimal cable length for a given scenario. And in this context, we define two cost functions, J2 and J4. J2 consists of only two performance metrics, the Q-tune and gamma integral normalized, and J4 consists of all four performance metrics normalized and equally contributed. And we swept the cable length from 2 feet to the 100 feet. And if you check the J2 versus J4 graphs, you can see a periodic movement, and you can see the currently using 77.3 feet cable, the standard default cable, consists of one of the worst case for both J2 and J4, which means that if we just cancel out the transmission line effect, we can do as good as the dashed black line. But if you check the figures, you can see that we can still go down in terms of the J2 and J4. We can still do better than the just canceling out the effect with the inverse of it. And if we check the optimal cable length, one of the minimum points in this J2 and J4 graphs, and select the smallest cable, shortest cable, it's around 29.6 feet of best cable case. And if we add it as the case 3, the golden scenario where we canceled out the transmission line effect with the inverse model and introduced the virtual cable with the optimal scenario, we can see that we did better than the best case scenario where we just cancel out the bad effects of the transmission line, which infers that we can still do better than the scenario. Instead of just canceling out the transmission line by the inverse, we can do better with the virtual cable. And if we check the scenario, the performance under the noise, you can see that if you compare the case 0 and case 2, we canceled out the Z transmission not 100% by just the inverse, but there's still some improvement in terms of the performance metrics with the effect of the noise. But if you check the virtual cable with optimal length, there is still better in terms of the both all of the performance metrics in a better way. Similarly, if we check scenario performance with uncertainty, we inject some uncertainty in terms of the model parameters like the transmission line properties or the impedance matching network properties. We can still see the similar behavior. By just canceling out the Z transmission effect with the inverse, we recover some of the performance, but by the introduction of the virtual cable with the optimal length, we have the best case scenario. And as the conclusion, the starting default cable length will give some negative effects on the system with the transmission line impedance. By just including the cascaded inverse transmission line, we can cancel out the negative effects. But this is not only enough. By introducing the virtual cable with the optimal cable length, we can do better than the best case scenario in terms of not just canceling out the transmission line effects, but also improving the performance accordingly. So thank you for your attention. If you have any questions, please proceed.